Okay, I'm hoping after you guys collected data on Monday, that you had graphs that looked sort of like this. Okay, and remember you had the card on the end of the track, you started data collection, and the motion detector started clicking, so you let go of the cart sped up, moved away, and got to the end of the track. Okay, well, the fifth step down here says to label each section of the graph above describing the cart's motion. Okay, so that's pretty easy. In fact, it's especially easy to do this since all these graphs are lined up, okay, and they all show the same motion. So for these first 0.6 seconds when I did this, this was the cart at rest. I hadn't let go of yet. I hadn't let go of it yet, so it hadn't started to move away. This next time interval, and I'm going to divide it up here, okay, is a little bit hard to see on the acceleration time graph or the position time graph, but on the velocity time graph it's pretty easy to see. This is the part where it's sloping up, and so this is where it speeds up and moves away. Okay, so I'm going to say speed up away, and it's not just describing the position time graph. You can see that in the position time graph because it's curving, right? It's getting further away and it's getting faster. We can see it in the velocity time graph because the velocity is down here at 0, but it's getting more positive, so it's speeding up, and it's positive, so it's moving away. And we can even see it in this acceleration time graph because we can see a positive acceleration, which means that the velocity is increasing. Okay? And then this last little time interval here, I guess there's really two, but okay, we're only interested in maybe this part of it. This is where it moves away constant. Okay, so constant away. Okay, and this was after that hanging mass hit the floor. It stopped speeding up, but it didn't do anything else either. So constant away for this interval, and we can see that on our position graph, it's a straight line. On our velocity time graph, it's a horizontal line. And on our acceleration time graph, it's a horizontal line on the axis, 0 acceleration. The velocity isn't changing. This stuff over here, not concerned about it, right? It got to the end of the track, it stopped, so its position didn't change. Its velocity went to 0. And we had this big negative acceleration spike because it had to slow down in a hurry. Okay, we're not really interested in that motion. We're mostly just interested in this portion right here where it's speeding up, moving away. That's what the next couple pages of this graph are about, or this lab. Okay, so these questions are pretty straightforward. How would the velocity time graph, what about the velocity time graph indicates the motion was away? Well, it was all positive, right? It was all above the axis. Wow, that almost looks like a word. Okay, so I'll try that again. Above axis. Okay, do it that way. What about the velocity time graph indicates the cart was speeding up? Slopes up, right? It started at 0 and it got further from 0, so we know it got further from the axis. It's speeding up. How would it be different if the velocity was constant? Instead of sloping, it would be horizontal, right? This last one, be careful. How would the xt graph be different if the velocity was constant? It would be straight, not curved. All right, so those are pretty straightforward. That's old information. Okay. Now these questions here says, all right, let's look at the acceleration and velocity time graphs and determine the average acceleration over the time interval when the acceleration is constant. Okay. Now that average acceleration, if I jump back and look at that average acceleration when the acceleration is constant, we're talking about this time interval right here. Okay, and we want the average acceleration of that. And the way I have it drawn on my graph, it looks like it's about 0.2, right? This value right here is fairly constant, and it stays right here at about 0.2. I don't know what it was on your graph, but it was probably right around there. Okay, and so you use the statistic feature on your iPad to actually get that. And so we've got whatever this is, and the units here should have been meters per second, which is a meter per second squared, and that comes from this math, right? When you divide fractions, you invert and multiply, so I have meters per second divided by seconds, which is times 1 over seconds, which is equal to a meter per second squared. Okay, so that's where that comes from. Also record the time interval over which the acceleration was constant. Again, if I jump back to that graph, what that means is I want the starting and ending times of when that happened. And on my graph, it's 1.4 and 0.8. But again, I just made these up. They're not canon. They're not real. Okay. Awesome. Find the slope of the velocity time graph over the same interval. Show your calculation below. So you're going to find the initial and final velocity from there. And so again, let me jump back to that graph. Okay. Since I picked this time interval for my acceleration, I would need to pick the same time interval for my velocity. And so if I just extend this line up, okay, what we're talking about is the initial and final velocities during this time. So I would say, all right, my initial velocity was right here, and it looks like I have it drawn as 0. My final velocity is right here. It looks like I have 0.6. Okay, and so I would record that information over here in these lines. Okay, and then to find slope, you're going to subtract final velocity minus initial velocity, final time minus initial time. And so careful on this one, right? It says, what are the units of these slopes? Well, you're doing meters per second for a change in velocity divided by seconds, which is going to be a meter per second squared. Okay, so these units match. And hopefully what you found was this mean, this average velocity right here that you got down here, they should have been pretty close to the same. Okay, and it's just like on a position time graph. The slope of a position time graph is velocity. Well, the slope of a velocity time graph is acceleration. And that's what this little box down here says. Okay, it says average acceleration can be found by dividing the difference in the velocities by the time interval it takes the velocity to change. So average acceleration is the slope of a velocity time graph. Okay, moving on. All right, calculating change in velocity from an acceleration time graph. So we know how to go from velocity to acceleration, right? From velocity to acceleration is just going from, it's graphing the slope. This one says, well, let's go the other way around. So it says, okay, resketch that acceleration time graph, and I can't remember. I think it looks something like this, and then, or whatever. All right, so there's my acceleration time graph. It says select a time interval for which the acceleration is positive and fairly constant. Okay, that would be this time interval again, right? It's positive, it's fairly constant. You want your initial time. My initial time is 0.8. My final time is 1.4. Okay, and then it said to find the area under this curve. And it said to do that by using the average or mean acceleration and use that to compute the area. Well, if you find the average acceleration during this time interval, it's going to have a value of about 0.2 because that, well, at least mine does. That's where it's drawn on this graph and it doesn't change. It's constant. Okay. Now that's not an area. That's a height. Remember, the area of a rectangle, area equals length times width or base times height or however you want to say it. So you've got to take the delta t times the average acceleration, and that will give you area. Okay, and again, this is not a surface area, it's just an area because we're multiplying a length times a width or a base times a height or whatever. But as units, we see we're going to take the acceleration, meters per second squared, times seconds. This seconds cancels that square, and we'll be left with meters per second. So it's actually a velocity. Okay, so first I had you calculate the velocity or the area under that curve. Then I wanted you to, on your velocity time graph that corresponded, find your delta V. Okay, and you probably had it from last time. And hopefully what you found was that the area you calculated here and the change in velocity you found here were the same thing. Okay, and so that leads us to this. How can change in velocity be found from an AT graph? Delta V equals area. Whoops, that's not how you spell area. Delta V equals the area under an AT graph. Okay, so hopefully that was not too bad. Hopefully you had some pretty good results for that. If not, you can either try again or we can talk one day and hopefully clear that up. Now this page, there's actually no data to collect. Okay, it's just telling you how to interpret an acceleration time graph. Remember when we went from a velocity time graph to a position time graph, I had to give you the initial position because a velocity time graph doesn't tell you how the or where the object's at, it just tells you its displacement. Well, the same thing is sort of true on acceleration. It doesn't tell you the direction the object's moving. All an acceleration time graph tells you is whether the velocity is becoming more positive or the velocity is becoming less positive. If the velocity becomes more positive, it's a positive acceleration. So this acceleration time graph describes every single one of these velocity time graphs, okay? Because really, it's the slope. An acceleration time graph is the slope of a velocity time graph. Since these all have the same constant positive slope, they all have the same acceleration. You'll notice this velocity time graph is all positive, so it starts slow and gets faster moving away. Okay, but the final velocity is more positive than the initial velocity. Here, it started actually with a negative velocity, so it's moving in a negative direction. It's getting closer to the origin, but as it's doing that, it's slowing down, right? Because its speed's getting closer to zero. Then it turns around, moves away from the origin, and speeds up. It's still got a constant positive acceleration because the whole time it's moving away, its velocity, or moving either direction, its velocity is becoming more positive. And this one takes it to the extreme case. The whole time it's moving towards the origin. So the whole time it's got negative velocity, but it's slowing down. And right, since -2 is less negative than -4, its velocity is actually increasing. It's becoming less negative. Okay. Similar things happening over on this side. Every time over here, the acceleration is negative, so the velocity becomes more negative. So it can move away the whole time and get slower. It can move away and get slower, switch directions and speed up, or it can move in a negative direction and while it's doing that, speed up. Okay, so all of these velocity time graphs have this acceleration time graph, and all of these velocity time graphs have this acceleration time graph. So that's just a little bit funny and hard to deal with. All right, and then there's this page. Okay, this page is trying to put that all in perspective. It says the slopes of tangent lines to an xt or position time graph can be positive, negative, or zero. However, the sign of the x value has absolutely nothing to do with how x is changing. So this graph is trying to say, okay, let's start with the position time graph, and let's get from that, let's figure out what the velocity is, and if we can figure out what the acceleration is, we'll be really doing good. Okay, so there's an xt graph, and we're supposed to fill in these columns based on the information in the graph. Okay, so first it says let's just get the sign of x, and to do that we just say up here is positive, below the axis is negative. So let's see, at A is right here, that's a positive A. B is over here, it's negative. C is over here, it's positive. D down here, negative, and then E is also negative. Okay, so we've just located, is it in front of the origin or is it behind the origin? That's all we've done. The slope, so these tangent lines are drawn here, so now we can find the sign of those tangent lines. Okay, and so at A, you see this line is sloping up, so it's a positive slope. Okay, at B, this line is also sloping up, so it's a positive slope. C is sloping down, it's a negative slope. D is sloping down, it's a negative slope. E has absolutely no slope at all, so it gets to be 0. This next column, okay, it says, is the slope increasing, decreasing, or staying the same? But you have to keep in mind sign matters. Both position, velocity, and acceleration are all actually vectors, so sign matters. We have to keep that in mind. So the easiest way to do this is say, all right, if I move a little bit further on, is this going to be a steeper line in a positive direction or a steeper line in a negative direction, or what's going on? Is it becoming less steep? So let's look at just A. Okay, A is right here, and it's sloping up. If I were to slide this just a little bit further over, it would go from a positive slope to almost a flat one. So that's becoming less steep, and I'm going to say then that it's decreasing, right? But I got to be careful, because if I move to B, okay, B is pretty intuitive. It's right here. If I move a little bit further on, that slope's going to be a little bit steeper. So that's increasing. Okay. Um, C is right here. Okay. If I move a little bit further right on this one, it's going to get steeper, but it's going to get steeper negative. It's going to become a more negative slope, and that means that it's decreasing. Okay. D. D is gonna, it's negative, it's gonna get less negative, right? It's gonna get a little bit flatter, it's gonna get less steep, but it's gonna do it in an increasing way because the slope is becoming more positive or less negative, however you want to look at it. E, sort of the same thing. It's 0 right now. If we move a little bit further right, it'll slope up, so that's increasing. Okay. Now this last one, the sign of the acceleration, well, I'm just looking right here. If this is decreasing, this is negative. If this is increasing, this is positive. If this is decreasing, this is negative. And let's see, if this is increasing, this, we got one more here. This one's positive, it's increasing. Okay, so the next part of this lab is going to summarize what's going on in each case of acceleration. Okay, so the next part of this lab says, all right, you need the cart and the tracks again, and you're going to collect data, in both directions. All right, good luck.